Hello all, welcome to tutorial for week 10 of quantum mechanics 1. So it's time, but let's wait for a couple of minutes so that if someone wants to join they can join, and then we can begin solving some problems related to week 10 course content. Hello Harshul. So let's wait a few more minutes so that if somebody else wants to join they can join.
Okay, sir.
Hello ma'am. Okay, I guess it's time we can start. So, before we start, do you have any doubts that you want to ask? No? Okay. Okay, so I hope my screen is visible and my audio is clear. Then we can straight away dive into solving some problems. Alright, so first problem of the day, what do we have? We have a state vector psi that transforms into another state vector psi prime by unitary transformation, and an operator A transforms as A prime. Now it is given that if A is Hermitian and then A prime is anti-Hermitian, and we have to tell whether this statement is true or false. So what is given to us is this statement that if an operator A is Hermitian, then its unitary transformation A prime is anti-Hermitian. We have to tell if this is true or it is false. Okay, so we already know what a unitary transformation is. So we okay, let's write what we are given. We are given that A is Hermitian, which means that A dagger will be equals to A. And let us consider a unitary operator U such that U dagger is equals to U dagger U is equals to identity. Okay. Now, so let us do the unitary transformation. So upon unitary transformation, it is given that we will get a vector, we will get a operator a prime by this transformation. So we'll have a on this side and we have dagger. Okay, so let's take adjoint. Okay, taking adjoint of this equation. Why adjoint? Because we have to tell whether this a prime is anti-Hermitian or not. So for anti-Hermitian, basically we have to find out this quantity and see if this is equals to minus of a prime. If this is true, then we can say that a prime is anti-Hermitian. So we are going to take adjoint, and what we will get is a prime dagger is equals to u a u dagger adjoint. Okay, now we know when we have to take adjoint of products, so their order is reversed. So this u dagger will come first and its dagger, then a will come next and its dagger, and finally u dagger. So this will be just simply u, and this will, so we know that this a is Hermitian, so a dagger is simply a, and this is u dagger. So what do we get? And so from equation, let's say this is equation 1, this is equation 2. So if we compare both these equations, the right hand side is the same. So we can say that a prime dagger is simply a prime, which implies a prime is Hermitian. Okay. And in the question they say that a prime is anti-Hermitian, so this statement is false. Okay, any doubts?
What did we do with psi, or it was just given us some information?
It was just given as a kind of a definition of a unitary transformation.
Okay.
Yeah, we didn't use that. That is not required. Okay, so let's move on to the next one. Here we have a wave function of an electron in a hydrogen-like atom. So we are given this wave function. Okay, so you can already see that it is a radial function. We don't have any theta or phi dependence, right? And this a is a naught by z, and a naught is the Bohr radius. Okay, so what we are asked to find the normalization constant c. So basically we have to normalize psi. So to normalize, okay, so to normalize, so first of all we have psi of r, c times e to the minus r by a. Okay, then the normalization condition would require, so normalization condition, this is the condition that our integral mod psi squared d3r, this is 1, right? Or we can write it as 3 different integrals. So this will be integral dr, this will be 0 to pi, so this will be integral d theta, and 0 to 2 pi. Sorry, here we will have 1 sine theta d theta, and here we have 1 d phi. Okay, and then so mod psi will be just mod c e to the minus r by a and squared, and also we will have 1 r squared. Okay, and this has to be equal to 1. So this quantity, basically these two integrals will just give us 4 pi, right? So this will just give us 2 pi, and this integral from 0 to pi will give us 2. So what we will then have, so we will have 4 pi integration 0 to infinity, and here we will have r square e to the minus 2r by a. Okay, and then okay let's take this constant c squared outside. Okay, and then dr, this is equals to 1. Okay, this is clear. Okay, so now let us call this integral as I. So if you know gamma functions, then you already know that this I is nothing but a by 2 cube and gamma 3. So gamma 3 will be nothing but 2 factorial, which is just 2. Or we can even solve this explicitly in case you don't know the integral form. So we will do integration by parts. So let this be I, and let also we will do let 2 by a is equals to k. So we have this k is 2 by a. Okay, so then our integral I is nothing but r squared e to the power minus kr dr. And so doing by parts, so okay, 0 to infinity, we will have minus r squared by k e to the minus kr 0 to infinity plus 2 by k 0 to infinity r e to the minus kr dr. Okay, so this, when we put the limit infinity, this term goes to 0, and when we put the limit 0, so the first factor goes to 0, so this term entirely goes to 0, and therefore we have I equals to 2 by k integral 0 to infinity r e minus kr dr. Again doing integration by parts, so we will have I as 2 by k, and this will give us minus r by k e to the minus kr 0 to infinity, and then this will become plus 1 over k integral 0 to infinity e to the minus kr dr. Okay, again when we put infinity, so this exponential term goes to 0, and when we put 0, so this r term goes to 0, so this entire term is again 0, and what we have is 2 by k squared, and integrating we get minus 1 over k e to the minus kr. So this is again 0 to infinity. So putting infinity will give us 0 because of this term, and putting 0, so we'll have, so this term will be 1, and this minus minus will become plus, so we'll have 2 over k cube. Okay, so this is equals to I. So here, then if we substitute, okay, also we can check that this, because this is nothing but a by 2 cube and 2 factorial, so which is just 2. Okay, and this 2 by k cube, and this, because we have k is 2 by a, so both of them are same. And then substituting back, we get, so we get, upon substituting back, we get 4 pi c squared, and k is nothing but 2 by a cube, right? This equals to 1, which implies 4 pi c squared, and this will become a cube, so this is 2a cube by 8 is equals to 1. So this 4 times 2 is 8, and they will just cancel out each other. So this simply implies that pi a cube c square is equals to 1, or c is nothing but 1 over pi a cube under root. Okay, so let's check. So option C. Okay, so it's just a more like an integral problem, so we just use this normalization condition, right? And then we solve this radial integral, and we just note that this d3r is nothing but r squared sine theta dr d theta d phi. Just put this thing in, and then we get our answer. Okay, so okay, so moving on. So here we are given that the eigenstate of Jx with eigenvalue h cut by 2 will be. So we are given the eigenvalue h cut by 2, and we are asked about the eigenstate of Jx. Okay, so let's write the eigenvalue equation. So the eigenvalue equation will be Jx operating on state psi half. So we will get h cut by 2, and again we will get psi half, right? So the problem is that we want to find what will be the value of psi half. Okay, so first of all, let me ask you that are we familiar with the form of Jx? So Jx has this form, h cut by 2, 0 root 3, 0 0 root 3, 0 2 0, 0 2 0 root 3, and 0 0 root 3 0. So this is the matrix form of Jx. Is h cut by 2 times this thing. and then let's assume that our state is unknown, so it is some ABCD, and then eigenvalue is h cut, and again we have ABCD. Okay. Okay, so let me quickly ask, do you want me to show how we get this form of Jx, or is this known to you?
Yes, please tell.
Okay. So, okay, let me quickly open a new page and then we'll come back here. Okay, so yeah, let's do it. Okay, so we know that this Jx, so generally we have to find this representation of Jx, so we use basis of j squared and jz, right? Generally we do this, right? We use the basis spanned by j squared and jz, right? That is when we get ll plus 1 and m, so we get the two eigenvalues. Okay, so let us consider j as 3 by 2. Then m will have 4 possible values. Okay, for j 3 by 2, m will have 4 possible values: 3 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. Correct? So then we can define our basis. So let us define basis. We will have 4 basis states. Okay, we will have 4 basis states. State 1 will be 3 by 2, 3 by 2. State 2 will be 3 by 2, 1 by 2. State 3 will be 3 by 2, minus 1 by 2. And state 4 will be 3 by 2, minus 3 by 2. Okay, so this is our basis states. Okay, so we have 4 element column vector. Okay, we have these 4 states, so we have a 4 element column vector. Fine. Now what we know ladder operators. We know that we have these ladder operators j plus minus, and when they operate on a state j comma m, what do we get? We get this thing h cut, and then big under root, sorry, j plus 1 minus m plus minus 1, right? And then the state goes to j m plus minus 1, right? So if we are doing j plus, so then our m is increased by 1. If we are doing j minus, then m is reduced by 1, right? So this is our final state. Okay, so in this problem we took j as 3 by 2, so j plus 1, which is 3 by 2, 5 by 2, 15 by 4. So this term is always 15 by 4, this first term. This is not going to change. Okay, now let us calculate for all these 1, 2, 3, 4 states, what do we get? Okay, so let me ask you, when we do j plus, let's do for plus states first, right? Let's do the raising operator ones. So when I do j plus on the state 3 by 2, 3 by 2, what will I get? What will I get?
It will go to 3 by 2, comma 5 by 2.
But that is not possible, right? Because m cannot have value greater than 3 by 2. Yeah,
So this should be 0 then.
this will
Should
be
be
0.
0.
This will be 0. Correct. So this state, so we cannot, basically we cannot raise this state. This is the highest possible state. So applying a raising operator will give us 0. Okay. So let's go to our second state, which was 3 by 2 comma half. So what will this give us?
The state will be 3 by 2, comma 3 by 2.
Yeah,
And
and a prefactor.
inside,
Yeah,
inside should be 15 by 4 minus of
15 by 4 minus of.
hmm,
So m is half.
by 2 into 3 by 2. 1 by 2 into 3 by 2.
Correct. And then taking the square root, this thing, and then 3 by 2 comma 3 by 2. Yeah, good. So this will be how much? So it is 15 by 4 minus 3 by 4. So 12 by 4, so root 3. Yeah. So this entire thing just becomes under root 3, and then we have one h cut. Okay, so let's do for the next one. J plus 3 by 2 minus half. Okay, so again we'll have h cut here, and this we know is 15 by 4, and minus of minus half becomes plus 1 by 2, and m plus 1 is again 1 by 2, right? So this is how much? 15 plus 1, 16 by 4, and then this state is 3 by 2 comma 1 by 2,
1 by 2.
right? And this, so this will be 16 plus 1, oh sorry, 15 plus 1, 16, 16 by 4 is root 4, so just 2, right? So 2 h cut. So this entire thing, it just becomes h cut and then simply 2. Similarly, let's do for our final state. So this was the last one, 3 by 2 comma minus 3 by 2. And this will go to, so here we'll have h cut, and here we'll have 15 by 4, and this will become plus 3 by 2, and then minus 3 by 2 plus 1 will give us minus 1 by 2. Yeah. Yeah. So this is again minus 3 by 4. Okay, and then the state here will be 3 by 2 comma minus half. Yeah. So this is again 12 by 4, so under root 3. So h cut times root 3 again. Okay, so let me quickly put them here. Okay, so this was the action of uh, raising operator, right? Similarly, okay, so what do we get here? So you can see that if I want to now construct a matrix, so the matrix elements, we know the matrix elements m I k, I'm not writing j, so m I k, so we have I and then j and then k. Okay, so this I and k, they go from 1 to 4, right? I comma k, They can be 1, 2, 3 or 4. So we'll get a 4 by 4 matrix. And these 1, 2, 3 and 4. So for example, this K state are these 4 states that we defined earlier. So this 3 by 2, 3 by 2 and so on. Okay, so what will our matrix, okay, so here, so what do we see here? So here we see that, so this is state 1, right? This is state 2, this is state 3, this is state 4, and operating on state 1 gives us 0, operating on state 2 gives us something which is written in terms of state 1, and this is written in terms of state 2, and this is written in terms of state 3. Okay, so basically when j, so when, okay, let me write it down. So the non-zero, okay, so the non-zero elements will be, so when we have state 1 here, and sorry, this will be j plus. When we have state 1 here and then j plus, this will only be non-zero when we have a 2 here, because this 2 will be raised to state 1. Yes, so here you can see this 2 goes to 1 when we apply this raising operator. Okay, so 3 by 2, 1 by 2, it goes to 1. So this term will be non-zero, and we know that this is under root 3 h cut. And then when we will have 2 here, we know that only non-zero term will be when we have 3 here. And similarly, when we have 3 here, only non-zero term will be when we have 4 here. Okay, and this we know is 2 h cut, and this we know is under root 3 h cut. So the matrix of j plus, so we'll have h cut outside. So here you can see 1, 2. So here we will have root 3 here, and this will be 2, 3. So here we will have 2 here, and then 3, 4, which means we'll have root 3 here, and then all other terms are 0. Okay, okay, this is clear.
Yes.
Good.
Yeah.
So then let me just get rid of all this, and similarly we can do for j minus. Yeah. Okay, or let me add another page. This is little in the derivation, but it's okay. Okay, so we have j plus. Okay, similarly, what do you expect for j minus? We expect the opposite, right? For j minus, because it is a lowering operator, so it will do opposite things kind of. So the non-zero elements that we will get in that case, so we should have 2 here and then j minus, and we should have 1 here, because the lowering operator will lower this state 1 to state 2, right? And so on for the other two also. So essentially for j minus, we'll get a similar matrix. So instead of 1, 2, the non-zero elements now will be at 2, 1. So here root 3, and this is all 0. This is all 0, this is 0, and now 2 will be here. This is all 0, and then we'll have root 3 here and 0. Okay, so you can check this on your own. So it's the same thing. We'll use this same equation and we'll do it for all 4 states, and you will see that we are getting the same thing. Okay, so now we have both j plus and j minus matrices, and finally we know that there is a relationship between j plus, j minus and jx. What is that relationship? So the relationship is that jx is half of j plus and j minus. Okay, so basically we will add both of these matrices, So we'll have root 3 to root 3 and then root 3 to root 3 like this, and then h cut by 2 comes outside. Okay, so this h cut by 2 comes outside, and then here we have 0 root 3 0 0 root 3 0 2 0, then 0 2 0 root 3, and then 0 0 root 3 0. Okay, so this is how we get jx. Good. So should we now move back to the problem? So here I have written the same form of jx. You can see we have these root 3 to root 3 and then root 3 to root 3 coming from j plus and j minus respectively. Okay, so now we can straight away cancel out this h cut by 2 terms. Yeah, so this h cut by 2 and h cut by 2, they'll just cancel out. And then let's do multiplication on the left hand side. So what we'll have here, if we multiply, so this first one will just give us under root 3 times b, and this one will give us under root 3 times a plus 2c. This will give us 2b plus under root 3d, and this will give us under root 3c, and this is simply equals to a b c d. Okay, so we have 4 different equations, right? We have 4 different equations, and then basically we will have some relations between these a b c d, and using that relationship between a b c d we will form our eigenvector. So the first equation, so the first equation will give us that we have under root 3b is a, and then we will have under root 3a, let me write here, we will have under root 3a plus 2c as b. Okay, and then we have 2b plus under root 3d as c, and finally under root 3c is d. Okay, so using these two, so this I will substitute here and this I will substitute here. So what do we get? So if I put a as under root 3b, so this will just become 3b, right? This becomes 3b plus 2c is equals to b, which implies, okay, 2c is equals to minus 2b, and we can cancel out these two, so this will just become c is equals to minus b. And substituting here, so this will be 2b, and if we put d as under root 3c here, so this becomes 3c. Okay, I think it will give us the same thing. So instead, now we have this relationship of c with minus b. So let's do d as under root 3, and instead of c we have minus b here, so minus b. So we have now also written d in terms of b, so minus 3b. Okay, and for a also we have under root 3b. Okay, so then our vector, this abcd, if we take b as 1, so our vector is of the form, if b is 1, so this will be root 3, this will be 1 minus 1 minus root 3, right? So this is what we have. And if we normalize this, so this state is not normalized, so what will be the mod of all these states squared? So upon normalizing, I think we will get, so this is under root 3, so this is 3 plus 3 6 and 1 and 8. So this mod square, so sigma mod ci squared is 1, and this is, so sorry, this is not 1, in this case this is 8. So upon normalizing, our state psi, we can write it as 1 by under root 8, and this under root 3, 1 minus 1 minus root 3. Okay, so let's look at the options. So there is no 1 here, minus root 3. Okay, so from normalization we know that it has to be,
I think A, because if you take B is equal to -1,
yeah,
then should be okay.
yes. So we can take minus 1 and then all these signs will reverse. So minus 1 minus 1 plus plus. So minus root 3 minus 1 plus 1 plus root 3. Yeah. A. Okay. So
Sir,
only, yeah.
so one doubt that I have is when we
Yes.
started off with it, we took j equal to 3 by 2, and thus we got f equals 3 by 2, 1 by 2, minus 1 by 2, or minus 3 by 2.
Yes.
So, how did you arrive at j equal to 3 by 2 initially?
Because if you look at the, okay, uh, I think it should be, first of all it should be given in the problem itself, but I deduced it because our state, so this has 4 elements. Okay, so if you look at our this eigenvector, you can see it is a 4 cross 1, right? So we have, it is a 4 element column vector. Okay, and then we have this eigenvalue h cut by 2. So therefore this matrix has to be a 4 by 4 matrix. So let's say if I take j as half, then j, okay, so j half will give me only a two element vector, right? Because then you will have only two possible values as m, so plus minus half. Okay, that's why I took 3 by 2, because then I know I'll have 4 states. So yeah, this thing is, this thing should be there in the problem, that this corresponds to j equals to 3 by 2 system.
And J is equal to 5 by 2 will have 6 elements.
Yes. So 5 by 2, 3 by 2, 1 by 2, 3, and the negative of these 3, so 6. So if for example this was a 6 element eigenvector, then we would have taken 5 by 2. That's it. That was the reason. Okay. Okay. Let's move on then. Okay, let's solve the next problem. And here we have this operator. We are given some operator O, I, J, X, J, Y, and then the expectation value of this operator. So here they mention clearly that J is half and M is half, and then we are asked to find the expectation value of this operator. Okay, so what is the operator? The operator, sorry, the operator is O. It is written in terms of iota Jx Jy. Okay. So now there are couple of ways to do this problem. Let me show you both. So one way is that we can write jx in terms of j plus j minus, jy in terms of j plus j minus, and then and then see what we get, right? So let's do that way first. So what we get here? So okay, so jx jy, what will this give us? This will give us 1 by 4 iota, and this will be j plus j minus multiplied by j plus minus j minus, right? So we will have 4 terms, 1 by 4 iota, and then we will have 4 terms, j plus plus j minus j plus okay, and then minus j plus j minus once again, yeah, and then finally we'll have minus j minus j minus. Okay, so what is this? This is commutator, right, of j minus j plus. So this thing is commutator j minus j plus, correct? And we know that this commutator has this value minus 2h cut jz cap. Okay, and this becomes j squared, and this becomes minus j squared. So we have 1 by 4 iota, this becomes j plus squared, and then we have minus j minus squared, and then finally we have this thing minus 2h cut j z cap. Okay, so this is the value of jx jy. Now if you want to find out the expectation value of the operator, so this expectation value so we have to multiply by I here, so this I and this iota will cancel out, so we'll have j comma m 1 by 4, and then this thing j plus squared minus j minus squared and minus 2h cut jz, and then this state j comma m. This is the expectation value. Okay, now tell me, when we do this j minus squared operator thing on this jm, we'll get 0, right? So this first term and this second term, this first term, it will raise it to m plus 1 2 times, so m plus 2, and because they are orthonormal, so this will give us 0. Similarly, this j minus 2 times will give us m minus 2, and because they are orthonormal, so this second term also will give us 0. Correct? So the only term that will sustain is the last term. This then will become, so this is 1 by 4, and so this will become minus 1 by 2. So this 2 and 4 will give us minus 1 by 2, and then jz acting on m will just give us m, and then no, it will give us m h cut, and we have additional h cut here, so this will be m h cut squared. Okay, this is clear. And in the problem it is given that m and j both are 1 by 2 1 by 2. So if we just put 1 by 2, if we just put what is m is 1 by 2, so if we put m as 1 by 2, So the expectation value is minus 1 by 4 h cut squared. So option D.
Can you repeat? Can you spell it down? Yeah. Uh, the third statement, j plus square and j minus square. Can you just repeat that? Why this is going to give us zero? J plus will act on the front one or the back one?
Back one. So for example, in this last problem, right? In this problem, when we are doing this j plus, you see what this j plus was doing? It was changing this m from, let's say, half to 3 by 2, or minus
Mm-hmm.
half to 1 by 2. So it basically j plus will do m to m plus 1. Okay, so j plus on this state j comma m will give you some factor here, and then the state j comma m plus 1, like this.
Mm-hmm.
Okay, and then on the left hand side, if you see this bra, it is always m, right?
Okay, so they are orthogonal.
They're orthogonal, so they'll not give you anything, so they'll just give you 0, right?
Okay, and the last term, minus 2 h j z.
Yes, so similarly, when we have jz, and then this acts on this j comma m eigenstate, we get this eigenvalue as mh cut, and the state remains the same, because this state is an eigenfunction of jz, right? This jz and j squared, right? These states are the eigenfunctions of these two, so these states does not change. Instead, we just get this eigenvalue mh cut. Okay.
Yes.
Yeah. Okay. So this was one way of doing it. Now we can, okay, so when you look here, that we have this iota jx jy, so this gives us one hint that if we instead use Pauli matrices, then this, instead of jx jy, if we have sigma x sigma y, so this operator is nothing but sigma z. Correct. So
Mm.
we can also approach this problem from the perspective of Pauli matrices. Okay, so let's do it. So, okay, sorry for that. Okay, so for, it is given that j is half, right? So we can write our jk as h cut by 2 sigma k. So j1 will be, sorry, jx will be h cut by 2 sigma x, and jy will be h cut by 2 sigma y, and jz will be h cut by 2 sigma z. Okay. Why? Because this is possible because when we have j as half, what is the dimensionality of our problem? How many possible states are there?
So
Two.
j m half and m minus half.
Yes, correct, exactly. So then we can simply use Pauli matrices because they are 2 by
So
2
but
matrices, so we can
yeah.
directly use them, right? This is why this Pauli matrix approach works here. Okay, so then our operator O, this is our operator. So what was it? It was I jx jy. So now for jx jy we'll substitute these things. Okay, so it becomes iota h cut squared by 4 sigma x sigma y. Okay, and we know that this sigma x sigma y, that this quantity is nothing but iota times sigma z. This is the cyclic relationship. Therefore this simplifies further too. So this iota squared will give us minus h cut squared by 4 and sigma z. Okay, now you can already see that we are almost there. So this O will be then simply minus h cot squared by 4 and then the expectation value of sigma z. Okay, so what will be the expectation value of sigma z for this state 1 by 2 1 by 2? The sigma z will be simply 1, so this state is, so this is just 1, and we easily get our answer as okay. So I mean this was much more simplistic. So here also if you see we kind of got the same thing, we only, the only term remaining was the z component, right? The x and y, they just vanished, only the z component remained, all other components vanished. And using the Pauli matrices we see that because this sigma x sigma y can be written in terms of sigma z, so only the z component will remain. So that's why we can get the answer much more quickly. Okay.
Expectation value of sigma z equal to 1.
Yeah. So
Okay.
this is 1. So you can check. You can. It's a very simple calculation. You can check. Okay.
Okay.
If you have any difficulty, then we will discuss in the next class. I mean, it's very easy to find the expectation value of sigma z. Just take the sigma z matrix. You already know the state. What is the state? State is 1 by 2 1 by 2. You know the sigma. Sorry, you know this matrix sigma z, and then just do the matrix multiplication. You will get 1. Okay.
Okay.
Okay. So okay, so let's take a small break. I'll have some water and then we'll continue with our next problem. Okay. So I hope you have already read the question. We are given that psi plus r and psi minus r are the eigenfunctions of the parity operator. So these are eigenfunctions, sorry, eigenfunctions of the parity operator, okay, belonging to even and odd eigenstates respectively. So even and odd respectively, and the statement is that these two states, they are orthogonal, and you're asked if this is true or false. So what do you think? Is this statement true or is this statement false?
Should be true.
It should be true. So how can you prove this? Okay. So intuitively we know that it should be true because they are eigenstates of this parity operator, and the parity operator is Hermitian. So this should be orthogonal states. But can we prove this mathematically? So let's first see what this parity operator does to psi plus and psi minus respectively. So when we have parity operator acting on psi plus, we get psi plus because this has even parity. On the other hand, if p acts on psi minus, we get minus psi minus because it has odd parity. Okay, so this is one thing. Now we also know that p is Hermitian, which means p dagger is equals to p. So let us consider, okay, one more thing is that this p square is 1. Okay, so if we operate parity twice, we get back to the same thing, right? That is why this p square is simply 1. So now let us consider this state psi plus and psi minus. Let's find out this value. Okay, so this psi plus psi minus, because p square is 1, we can write this as psi plus and parity operator 2 times psi minus. Correct? We can write it like this. And what we can also do is we can write it like this. You can do p acting on psi plus and p acting on psi minus. Why? Because p dagger is p. So we can take one of the p here and take it to the ket space. Sorry, we take it to the bra space. So this will not change, right? So this first term will give us simply psi plus, but the second term will give us a minus sign. So this thing. Okay. So now if you compare this left hand side and right hand side, so this value psi plus psi minus is equals to minus of psi plus psi minus. Okay, so I can write as 2 psi plus psi minus is 0, or simply psi plus psi minus is 0, which proves that psi plus is orthogonal to psi minus. Okay, because their inner product is 0. Therefore this statement is true. So what did we do here? We started with finding out the inner product, and we want to prove that this inner product is 0, right? That is when this will be orthogonal. If this inner product is coming out to be non-zero, then they are not orthogonal. So then we use the property that this p square is 1, so very cleverly we put 2 p's here, and then one p we take it with psi plus and the other p we take it with psi minus. So with psi plus we get psi plus, with psi minus we get an additional minus sign, and because of that additional minus sign, the orthogonality condition must be true. Okay, any doubts in this one?
If we take the inner product of psi minus with psi plus,
We'll get the same thing.
because in just thinking, because in that case, in
Yeah.
step 2, when you shift P parity towards the left hand side,
Yes,
then P is Hermitian, so P will remain P, but psi minus when it changes
because
will
okay,
there,
I
but
it will not change. So okay, I'll use another
it
color.
is not
Let me write
complex,
this
is it
as
not?
minus. Let me write this as plus. Right?
Uh-huh. Uh,
So this is minus, this is plus,
yeah.
and this is minus, and this is plus.
This first term, will there be any change of sign or no?
Which one, ma'am?
Psi minus, if psi minus is a complex number,
But this is so this minus one. So the uh this sorry this
psi is
eigenvalue.
a complex,
Yeah,
psi
size
is
complex.
complex,
Correct.
then it will be psi star.
But we'll keep it like this only. We'll not take it to the right. We'll not take it to the ket space. We'll keep it in the bra space. Only thing is the eigenvalue is coming out to be minus one, which is not a complex number. So if we take this thing, this remains minus one, right? Because there is no imaginary part here.
Yeah, but what about psi? Psi is always a real function.
No, no, psi can be complex. So
Psi can be complex.
yes,
So
psi can be
psi
complex.
minus when it shifts, so it becomes psi minus star.
But we are not going to shift it. So okay, so here on the left hand side. Okay, ma'am, wait a minute. I have to take one call. Sorry.
Okay.
Hello. Hi, sir. Actually, I am in a class, but I'll send someone, and someone will come pick you up and take you. Yes, yes. I'll send. If you can come to the lab, I'll send someone to the lab itself. Okay, sir. Wait for a couple of minutes, and somebody will be there. Okay, thank you. हेलो भाई कहाँ पे है भाई नीचे लैब चला गया वो गोपीनाथ आया है मैं क्लास में हूँ ओके भाई थैंक्स हेलो
Yes.
yes sorry so ma'am what I was saying that because now we have considered this psi minus in the bra space and psi plus in the ket state in this yellow markers, right? So on the right side also we'll keep the same convention. So we'll keep psi minus in the bra space and psi plus in the ket space. So this psi minus remains psi minus, and here also it will remain psi minus. Here also it will remain psi minus. It so we only take the complex conjugate when we take psi minus from bra space to ket space, right? Here it remains in the bra space itself. If I was to, instead of writing it as bra psi minus, if I wanted to write now change this to a ket psi minus, then I would take the complex conjugate,
Okay.
right? Then
So
then this start thing will come. Yes, ma'am.
when you are from like it is psi minus
Yes,
straight line,
yes,
then P. So you are shifting P from the right side to the left side. So in that case, only P will change to P dagger, but
yes.
psi minus will not change. This is
Yes, I
what you
will
are
not
saying.
change. Yes, exactly. Because we are not changing, we are not shifting
Yeah,
psi
I'm get
from
yeah.
one space to the other.
Okay,
It is remaining in the same space.
okay, okay.
And
And
what helps us here that this p dagger is p. So no
yeah,
matter in which space we take it remains the same because it is Hermitian.
okay,
Okay.
understood. Yeah, thank you.
Okay. Okay. So for the okay, so for the next one, we have an electron of mass m and charge minus e. So we have an electron, right? and it moves in a region where uniform magnetic field B del cross A exists in the z direction. So we have a magnetic field whose x and y components are 0 but z component is non-zero. So then the question is that the Hamiltonian can be written as, okay, so what we have, okay, so first of all we know that B is del cross A, right? So we can write it as, so the I component, this will be del Az del Ay minus, sorry, not Ay but del y, and then del Ay del Z plus the j component del Ax by del Z minus del Az by del x, and finally the k component del Ay by del x minus del Ax by del y. Okay, so I have just taken curl of this vector potential A. Now because the field is only in the z direction, so these first two terms they go to 0, right? So this term is 0 and this term is 0, and I have only the z term that should remain. So when will this be non-zero? This should not be 0. So what should be the form of my vector potential? So if I have my Ax as 0, my Az as 0, and then my Ay, if I write Ay as some b times x, right, such that my vector A is b x j cap. If I choose this A, then what will happen? So this first term, because Az is 0 and here this Ay is a function of x, so this will go to 0. So this first term, Az is 0 and Ay is a function of x, so its derivative is z is 0, so this term goes to 0, and here Ax is 0, Az is 0, so this goes to 0, and here Ay, okay, so this is bx, so this will just give me b, and this term will go to 0, so I'll have b k cap, right? So if I take A as this thing, then my b will be b k cap. Okay, just one second. Hello? वो तो OCCT में भाई चेक कर ले यार, मैं टी चेक करूँ, चलो ओके. Hello? Yeah. Okay, so then we have this thing. So then, okay, in that last class, we had also written our conjugate momenta, if you remember. So our conjugate momenta was basically this thing, P plus E by C A, right? And so therefore our Hamiltonian H will be 1 by 2m, so, and then square of this thing. So this will correspond to our kinetic energy, basically P squared by 2m. Okay. Okay, sorry for that. Okay, anyway, so we can what we can do, we can expand this bracket. So these are vectors, these are vectors, and what we'll get here, we'll get, so this will give us px squared plus py squared plus pz squared plus e squared by c squared a squared plus e by c p dot a plus e by c a dot p. We'll have all these terms, and therefore we can write this as px squared plus py squared plus pz squared, and this thing, so our a squared is b squared x squared, right? So e squared b squared x squared by c squared plus e by c py bx, because only the y component of a is non-zero, and then e by c bx py. Okay, so basically we'll have px squared, and so we have py squared here, and this quantity squared, and then we have 2 times py bx e by c squared. So we can write this as py plus ebx by c whole squared, and finally pz squared. Okay, so this is the form of our Hamiltonian. If we look at our options, so it matches with option A. Okay, so we have px squared and pz squared separately, and then we have this py plus ebx by c.
If we start with the taking a y as 0 and a x as by.
Okay, yeah, we can do that.
I think we should get a similar thing.
Yes, yeah, you're, so if, so basically you want this term to be non-zero, so if we put a as by, I think one minus sign as well, right? Yeah, so then this term goes to 0, and this term goes to 0, this goes to 0, and this goes to 0. Yeah, this will, so this will also give us b as b k cap. Correct. And then, so then here this term will remain same, and this term will also remain same. So here everything is same. So here instead of x square we'll get one y squared, right? So this will be y squared, and here instead of bx we'll get minus by, and again here also minus by, so that will be minus 2 by. Yeah, so in that case our Hamiltonian will have this form: px squared plus then, okay, so it was minus by. Okay, 1 second.
That is px minus eby by cv whole square. Okay.
So this will be, okay, so this we took along So okay, now here we will take ax, right? Ax, so it will be along I cap, right? So a will be along I cap. Okay, so it will not be px here. Sorry, it will be px minus e by by c squared, and then plus py squared, and then pz squared. This thing. Okay. So I mean it's the same thing, right? Because we know that we can always use gauge transformations, and using gauge transformations we can basically we can change our a, right?
Yeah.
Yeah, so both of these Hamiltonians will not change the physics of the problem. So anything we do, like the expectation values or anything, we'll get the same result.
Yeah.
Okay, so both are correct, I think.
Right.
Yeah. Okay,
Sir,
so yeah, sorry.
I'm slightly confused with how we got that square term py plus ebx by c whole square. That
Okay.
part,
Okay, so for that, if you if you expand this term, what you will get? You'll get 1 py squared, right? Which is here. You'll get this e squared b squared x squared plus c by c squared, which is here. And then you'll get 2 times py ebx by c, which is here.
and we took ay equal to bx.
We took ay equals to bx. Yes, here. Okay. Okay.
Yes.
Okay. So let's do the next one. So here the question says that classically rotational energy of a molecule is given by this thing, right? Where I is the moment of inertia of the molecule, and v is the number of revolutions per second. So this is nu. Okay. Nu is the number of revolutions per second. Now moving to quantum mechanics, if such a rigid diatomic molecule is in the state L is equals to 2, so we are given that the diatomic molecule is in the state L is equals to 2, then the number of revolutions per second will be. Okay, so classically they say that the energy E is 2 pi squared I nu squared. Okay, and then quantum mechanically they are asking like what will be the nu. So how much revolutions per second will our molecule make? Okay, so yeah, let's do it. So what is, so let's first of all we have to find out the energy. So quantum energy. So quantum mechanically. So our energy E we know is L plus 1 h cut squared upon 2i. Okay, so how do we get this thing? Yeah, you want to say something? Okay, so what I have done here, okay, what I have done here, we know that E is p squared by 2m. So if we multiply by r square here and here, so this becomes angular momentum. So this becomes L squared, and this becomes moment of inertia. So 2i. Okay, and then this L squared we know will give us this eigenvalue L plus 1 by h cut squared. Therefore we can write it like this. Okay, so this is the quantum energy. Now for L is equals to 2, what will we get? For L is equals to 2, our energy becomes, so this is 2 into 3, 6 h cut squared by 2I, or 3 h cut squared by I. So this is our energy now. Okay. Now if we use this equation, that this energy is equals to 2 pi squared I v squared, so what we get? We get 2 pi squared I nu squared is 3 h cut squared by I. So what we will get? So we will get nu squared will be, so this will be 3 h cut squared upon 2. Okay, okay, 6 h cut squared upon 2 pi upon 2 pi squared, sorry, and then I squared. Yeah, right, okay. So then I think if you look at the options,
So it is D, I think.
sorry,
It should be D, no? D. From here, we should get D.
so we'll get h cut by I under root 6 by 2, and this okay, let's
Under
write
root
as, yeah,
by
yeah,
2 is under root 3 by under
correct,
root
correct.
2,
We
right?
can write this as 6 by 4.
Yeah.
Yeah, let's do this, and then we can take the square root. So this implies that nu is nothing but under root 6 h cut by 2 pi squared, sorry, not squared, but simply 2 pi I, which matches with option D. Okay, so this much revolutions per second. Yeah, any doubts?
The formula of energy L into L plus 1 into h cut square by 2y
Mm-hmm.
in amount of energy. Was that a standard formula?
Yeah, so, oh, okay. So there is a problem in quantum mechanics. So like we have a 1D potential, right, in the x coordinate. So we there is a problem called rigid rotator. Okay. So hmm. Okay, I mean we can also derive this energy, but for a rigid rotator, for example, a diatomic molecule, the energy is written generally in terms of moment of inertia I, right? So okay, let me ask you. So also classically, if you have a rod or any object, so what will be its kinetic energy? Ke,
Half I omega square would be there.
right? Half I omega squared, right? So if I now wanted to write in terms of angular momentum, right? Just like how we convert this uh, half mv squared, right? We convert this to p squared by 2m. We can do the same thing here, correct?
You mean L square by 2y?
Yes, L squared by 2i. So this is the same thing. So this numerator is nothing but L squared,
Right, sir.
right? This is L squared and this is 2I.
Okay, okay, got it.
Got it?
Thank you, sir.
Okay.
Where are we considering the diatomic molecule?
Yeah,
Only in
so
the refrigerator?
yeah, so basically what we are considering, okay, so if you look at the problem again, so we are considering the rotational energy of a molecule, right? Only the rotational energy. So if we have a diatomic molecule like this, we are considering that it is just there is just rotational kinetic energy. Therefore, we are just worried about the angular momentum part, and therefore we can consider it like a rigid rotator. Rigid meaning that this distance will not change, as is expected for the diatomic molecule. Okay? And then rotator means that it will rotate, and it does not matter about which axis it rotates, because that will be taken care of by the moment of inertia. Right? So if it rotates about this axis, then the moment of inertia will be different as compared to that axis. So our nu has this moment of inertia. So we we do not need to define the axis of rotation to find out nu, because that will be taken care of by moment of inertia.
Okay.
Okay. Okay. So let's move on then. Okay. So now here we are given a harmonic oscillator, and the Hamiltonian in dimensionless units is written as this thing. So H is a dagger minus half, and the criteria for operations are defined as this thing. So this is a and this is a dagger, and then we are asked that the energy eigenfunction of a state is this thing. So we are given an eigenfunction, and we are asked that what is this n. So you see that here we have a small n, and the question asks what will be this n. Okay. Now, okay, so this thing is fine, but if you see this pre-exponent, and if you know that for a harmonic oscillator, this this pre-exponent is a Hermite polynomial, then you can directly guess the answer just by looking at its form. Otherwise, we can also solve this thing. So let me tell you both. Okay, so
Second is A or B. Can't
A
decide
or
which one.
B. Okay, let's first write the Hermite polynomials. Okay, so what are our Hermite polynomials? Okay, let me write here itself. So h0 is 1, h1 is 2x, h2 is 4x squared minus 2, and h3 is 8x cubed minus 12x. So you don't need to remember the numbers. The numbers are not important. Just look at x. So here we do not have any x. Here we have x, and then we have x squared minus x to the 0, and then here we have x cubed minus x to the power 1, and so on, right? And
Right.
you can see that this is of the same form. So for example, here I can take 4 as a common factor, and then I will get the exact form 2x cubed minus 3x. Okay,
Right.
so this directly tells us that this answer will be n is equals to 3. In case you happen to remember your Hermite polynomials, then the answer is directly, I mean, you can directly see the answer that this is going to be true.
Hmm.
Otherwise, we can also make use of all this other information that is given to us and try to find out uh, what is the most likely value of this n. Okay, so for that, we know that when this a lowering operator acts on n, we get under root n and n minus 1, and when this raising operator acts on n, we get n plus 1 n plus 1, right? Then we also know that a dagger n will give us 1 by root 2 x plus d by dx, 1 by root 2 x minus dy dx. Okay, why? So what we have done, so here a and then this iota p, so we know that p is of the form d by dx, and here we are taken this m h cut omega, everything is 1, right? It is given as this is a dimensionless units. So we have taken 1 by root 2 outside and 1 by root 2 outside, and then this is just, this thing is just x plus dx and this thing is x minus dx. So our a dagger becomes this, right? And then this our n is psi of n is this thing. So 2x cube, let's write this, 2x cube, sorry, 2x cube minus 3x and then e to the power minus x squared by 2, right? So let's see what we get when we do this operation. So first of all, this 1 by root 2, 1 by root 2, this will become 1 by 2, right? And then this will remain x plus d by dx. Okay, and when we operate this thing, x minus this x d by dx on this thing, so what we'll get? So first of all, so this we'll get, basically we'll get two terms, right? So one will be this 2x to the power 4. Okay, let's write it out. So 2x to the power 4 minus 3x squared and e to the power minus x squared by 2. So this will come because of this x term, and then we'll have minus, and then we'll differentiate these two. So differentiating the first one will give us minus 6x squared, right? 6x squared, and minus 3, and then the exponential term. Okay, and then we'll keep this first term same, 2x cube minus 3x, and we'll differentiate the exponential term. So again we'll have the same exponential term, and derivative of this will give us minus 2x by 2, so minus x. Yeah, okay, so let me simplify this a little bit. So x plus d by dx comes here, and then in brackets, so let's take out this exponential term outside, so e to the power minus x squared by 2, so this term comes outside, and inside then we have 2x to the power 4 minus 3x squared. Okay, and this will give us 6x squared, okay, minus 6x squared and plus 3, and this, okay, we have one minus sign here, so this will give us minus 4 x to the power 4 plus 3x squared.
Sir, over there, shouldn't p value be minus I h cut dou by dou x that we are substituting into this creation and annihilation operators?
Yes. So
But
yeah,
h cut is not visible anywhere in.
because the problem says that work in the dimensionless units, we can take m h cut omega, we can take everything to be 1.
Okay.
Okay, that's fine. Okay. Okay, so we have this thing, and then we have also minus 3x squared.
That minus 4x to the power 4 is, I think, plus 2x4.
Ah, yes, sorry. And this minus minus will make it plus, so this will be plus 2x to the 4th. Yeah, sorry. Because we have this 1 minus sign here and 1 minus sign here, so this will be 2x to the 4th. Yeah, okay. So we have this term, so we can, let me write this e to the power minus x squared by 2. So this will be 4x to the 4. This will be minus 3 minus x minus 3 minus 12x squared plus 3. Okay. Yeah. So then again, now we have to do this thing again. So what do we get this time? So
And this is, I think 4x square, 4x4 minus 6x square minus 6x plus 3.
no. Okay.
Is it?
No, no, no. See, we also have this minus x here, so that will multiply with this thing, so we'll not have any x term, so this will give us x squared, right?
When we are differentiating
Yes, ma'am.
in that 6x square minus 3, that should be 6x. Acha, okay, 6. Okay, okay. Sorry.
Okay.
Okay.
Okay, I think this is correct, but yeah,
Yes.
you can check.
Yes, yes, yes. This is correct.
Okay, okay. So then again, let's do this exercise once more. So this, let me just take this thing outside. And then when we have x, so this will become 4x to the 5 minus 12x cube plus 3x, right? So x will do this, and then we will have the differentiation. So we have taken, so let's differentiate this thing. So that will give us 16x cube minus 24x, and this is just 0. And then we will have one more term where this all will remain same, and only upon differentiating we will get a minus x multiplied with this, right? So minus x. Okay, hopefully we are doing it correct. So e to the minus x squared by 2 over 2, and inside, okay, what we have, so we have x to the 5, and then here also we will have x to the 5. So this is 4x to the 5, again this will be minus 4x to the 5, so x to the 5 term goes to 0. Let's look at the x cube term. So this is minus 12 plus 16, so this is 4x cube, and then this is 4 plus 12, 4 plus 12, so this is 16x cube. Okay. So this is plus 3x and minus 3x, so then this both of them will cancel out, and we'll have minus 24x. Okay, so if I cancel out with 2, if I cancel out with 2, so this will be 8x cube and this will be 12x. So if I look at this thing, okay, good. So then I can take 4 outside, and this becomes 4 2x cube minus 3x, right? And then the same exponential term, e to the power minus x squared by 2, right? Good. So ultimately what we get the same thing. So this 2x cube minus 3x and exponential same thing, so we get the nth state back. So if I, okay, let me write here. So when we do this operation, when we do a dagger n, what we get? We get 4n. This is what we are getting, right? Yeah. And then using these two, so basically we know that this a dagger is nothing but the n plus 1 times the number operator, right? We know that a dagger n gives us n plus 1 n, right? So on comparing, we get n plus 1 is 4, which means n is 3, right? Yeah. Okay. Any doubts in this? Okay, if not, then
Because the
yeah.
relations are Hamiltonian over there, sir,
Sorry?
but we did not use h equal to a dagger minus half anywhere in the question.
Yeah, we did not use that.
Was it just a distraction?
I mean, it's so okay. So we are not used to seeing it in this form, right? We are, because here, as you said, we don't have any h cut or omega or anything, right? So here, if you
Oh,
want, okay, what is the Hamiltonian? Otherwise, okay, or even the energy, it is n plus half. Oops, sorry. It is n plus half h cut omega, right?
yes,
So if you take h cut and omega everything 1, so what we get? We get E as simply n plus half, right? Now if you
right.
compare these two, the Hamiltonian and the energy, you can clearly see that this a dagger will give you n plus 1. Only then these two will match, right? Because here you have minus half, so we'll need n plus 1 to counterbalance this thing. Okay.
Yes, sir.
So in this sense you can use this, but if you already know this, then not necessary. Okay.
Okay, sir.
Okay. Yeah. So another true or false question. So we are given that x prime and px prime are the coordinate and momentum after time reversal. Then the fundamental commutation x prime comma px prime is minus h cut. So is this statement true or false? What do you think? Okay, first of all, the fundamental commutation. What is the fundamental commutation before time reversal? So x comma px. What do we get here? Just I attach cut. We don't have any minus sign here. So the question is asking that if we apply time reversal, then will we get a minus sign or not? That is the question. Okay, so our x prime comma px prime, this we can write as the time reversal operator and again the time reversal on momentum, right? And we know that the position is invariant under time reversal, so x remains x, but we also know that the momentum changes sign upon time reversal, so this becomes minus px, right? So we can write it as minus x comma px, and this we know is iota h cut, so this becomes minus iota h cut. So this statement is true. Is this clear? Yeah, okay. So then let's move on to the final problem of the day. Okay, so here we have here we have to find out this value. Here we have j plus squared and jz. Okay, so here we'll make use of the commutation. Okay, so the commutation relation, we know that j plus and jz commutation gives us minus h cut j plus. Okay, so I'm assuming we know this. Okay, then 1 0 j plus squared comma jz commutator, and then 1 0. So this then we can write as h cut 1 0 so this becomes j plus comma jz, again let's not write it, this thing, right? And then plus j plus comma jz and j plus and again 1 0. Okay, so what I have done, I have written this j plus squared as j plus times j plus, and then this expanded this commutator into two terms. So in one term this j plus comes first outside the commutator, in the second one this j plus comes second. Okay, now this commutator we already know, j plus comma jz, so we'll just substitute it, and what we get, we'll get minus h cut 1 comma 0, so this will become j plus j plus. Similarly this will become j plus j plus 1 comma 0, so this becomes minus h cut 1 comma 0, okay, minus 2 h cut 1 comma 0 j plus squared 1 comma 0. Okay, so what will we get when we operate j plus square twice on this state?
It should give 0.
Yeah, we'll get 0 because this state will be raised 2 times, and because of orthogonality, so this term goes to 0. So this
In
entire term
fact,
goes to 0.
this after first j plus, the second j plus operating on 1 1
Yes,
will also give 0 because m cannot exceed
correct.
j
That is
plus.
also true.
So
Yeah. So I guess it's time. Yeah. So I mean there are only 5 minutes left. So and I don't have any other questions today. So if you have any doubts, I can stay here for 5 more minutes. Then we can discuss those doubts.
In week 11,
Week
it is
11.
CZ coefficients. Will you be taking in the next tutorial next week? CZ coefficients, Flesh,
Okay.
Gordon.
Yeah, Clebsch-Gordon coefficients. Yeah.
Next week
So
is it
CG, CG you mean, right?
CG? हाँ, CG, CG.
Yeah. Yeah.
And
Yes.
reducible and irreducible basis or reducible and irreducible states. That is
Mm-hmm.
also for the next week.
Uh, that one I'm not sure. Yeah, I can. Okay. I'll include 1 or 2 questions for that.
Next time, next time.
Yes, next time.
Okay.
So the CG coefficients and the reducible, irreducible states.
Okay.
Okay.
Sir,
Yes.
in the previous question, what we
Previous
did
question.
was
Previous
time
question is this one. Yeah.
time reversal.
Yes.
So this time reversal part, I did not understand what time reversal means and what we are doing over here.
Okay. Okay. So if you remember, in one of the previous tutorials as well, we discussed that if you have, let's say, this is your particle, and this is your, let's say, origin, and then this is our x-axis, and then it is moving that it is moving in the plus x direction, right? So at 1 second it is here, at 2 seconds it is here, at 3 seconds it is here, right? So you record this and then you rewind this thing. Okay, so time reversal is basically just rewinding this thing. So when we rewind it, so your particle will be here 1 second earlier, your particle will be here 1 second earlier, and then here even like 3 seconds earlier, right? But the direction of its velocity will be here, like opposite, right? You'll see that it is moving in a opposite direction, correct? So from
Yes,
this you see that your x value does not change, right? Upon reversing the time, your position is same, right? So this x0, x1, x2, they remain exactly the same. However, your momentum gets a minus sign. So earlier, if your momentum was px was greater than 0, or let's say just give it some number, like let's say this was plus 2. So now your momentum after time reversal will be minus 2, because now you'll see that it is going in the minus x direction. Okay. So basically, when you do this time reversal operation, your x will not change, right? X remains x, but your momentum gains a negative sign. That's it. Now I can ask you further. Okay, so what do you think will happen to the energy?
energy, it would be p squared by 2,
Yeah.
but p square would be positive even if it.
Yes. So your energy is also invariant under time reversal. Correct.
Sir, but position, if you look at it,
Yes.
at time t equal to 0, it was at x equal to 0 initially.
Yes.
But now at time t equal to 3, it's at x equal to 0. That
No.
finally comes.
No. No. No.
Okay, Manu,
Is
I'm ready.
Yeah. Okay, ma'am. See you next week. Bye bye. Okay, so we are not seeing at it's not at time t equals to something. Uh, That's not the correct way to look at the problem. So that way, even the momentum is something else, right? So here, okay, how do I say this thing? I mean, I get your doubt, but when we reverse the time, so your t. Okay, let's say let us give it some timestamp. So let's say this is time. Sorry, this is time 0. This is 1. This is 2. Okay. and we are moving in a positive time direction, right? So increasing time, and then we record this thing. Okay, so everything is fine. And then when we reverse this thing, so the timestamp that you will see on your video will be will remain the same. So they will remain 210 only. Okay, it will not be 012.
Okay.
Okay, so it's like time frames. So those will not change. But what you will perceive is that your particles has started moving in a opposite direction. Correct?
Yes,
Yes. Okay. Any other doubt that you want to ask?
sir. I think most of them are.
Okay. Okay. Then I'll see you next Saturday. Okay. Have a nice day. Bye bye.
Bye.
Bye.